Welcome back to the show, team. My name's Amelia, and today we have yet another awesome guest on the show, and I'm very, very excited to, yep, we can have a great chat. We have Dr. Eleanor, who is a biochemist. Welcome to the show, Dr. Eleanor.
Thank you for having me.
It's an absolute pleasure, and I'm very excited to ask this question. What is your job?
I think I know why you're excited because you know what I'm going to say. I work at the Science Donut. Yeah, I'm an instrument scientist working at the Australian Synchrotron, which we lovingly refer to as the Science Donut because it's a big donut shaped building. And I spend my days sort of wrestling with different subatomic particles, trying to make them behave and help other researchers get the best possible results from their experiments when they come to visit us.
Now, I did just introduce you as a biochemist, though, and now
Yes.
I'm like, now I feel like I've misled everybody. How is the biochemistry sort of linked to the synchrotronness?
So that's a really good question. I am biased when I make this assertion, but I think it's fair to say that synchrotrons really exist because of biochemistry initially. So they've synchrotrons have lots of applications in all kinds of different fields, but initially the sort of premise of the synchrotron was to generate ultra bright light to look at samples of protein crystals. So, this is a technique that has been used for about 100 years. Shoot x rays through a crystal of a protein that you're interested in, collect the information out the other side, and that allows you to build a three-dimensional model of that protein. And that kind of information is really important to scientists who are looking at things like designing drugs that are going to interact with a particular protein, or looking at how two different proteins bind to each other, or even just fundamental things like, how does this particular shaped molecule alter a protein, and then all the knock on effects in metabolism from there. So they're kind of, there's this really long lasting link between X ray technology, synchrotron radiation, and being able to see biological structures in three dimensions.
There's a lot of things in there that I feel like we need to follow up. Did you just say that like we've been shooting X-rays at protein crystals for like 100 years?
Yeah, basically,
That's it.
it's
For some reason, I sort of thought, I don't know, since the 70s, maybe.
yeah,
Uh,
it's been a time. Yeah, so X-ray crystallography, which is what I do at the Science Donut, just recently celebrated its centenary. I say recently; it was a little while ago. The technique itself, people have been using for close to 100 years, a bit over 100 years, to investigate the structures of all kinds of different crystalline things. So not just proteins, but also like minerals and chemical crystals and anything that has that crystal property. It was actually a pair of Australians from Adelaide, the Braggs. So William and Lawrence Bragg were a father and they were from Adelaide, and they sort of pioneered this technique in the real early days. They got a Nobel Prize for it. And yeah, it sort of has this really long history. I'm just going to start throwing interesting facts at you, like the fact that Margaret Thatcher was trained as an X-ray crystallographer.
wow, there's a field to be. Wow.
So it's
Okay.
it's it's a really long-standing thing, and it's evolved a lot in terms of the technology that we have. So it's sort of unrecognizable today compared to what it would have been 100 years ago. My favorite sort of historical crystallographer was Dorothy Hodgkin. She solved the structure of insulin, which is a really biologically important protein. Anyone who has diabetes and needs to regulate their blood sugar using insulin, that's the structure that she very famously solved. She also looked at a lot of vitamin structures. And back in her day, to take this sort of information, so she'd line up one of these protein crystals, maybe a crystal of insulin, line it up with an X-ray source, which were sort of floating around in these labs, sort of in Cambridge and Oxford and those sorts of standard physicsy places, and each frame of information. So she'd switch on the X-ray, it would shoot through the crystal, diffract onto a photographic plate, and they'd actually expose that photographic plate for however long. They'd have to then take that plate away, bring in a new one, rotate the crystal a degree, fire the X-ray again, collect another plate of information, go back and repeat this sort of to get 360 degrees of the crystal. And then by hand, do all the mathematical transformations required to take those sort of beautiful scattered diffracted X-rays from that crystallographic sort of plate and rebuild the three-dimensional structure. So when she was looking at the structure of insulin, she collected the data in the 1930s and she solved the structure in the 1960s. So it was sort of a
Far
30-year
out.
process. To put some context of what we do at the synchrotron, we could collect an entire data set in 18 seconds and solve it in a few minutes. So that's sort of the difference in the scale of what we can do thanks to advances in technology over that 100 years. So I kind of went on a big old ramble.
No, that was beautiful. And yeah, I want to know what the ratio is of like how much faster it is now, because obviously it's a lot faster.
Mm.
That's She was dedicated.
Yeah, she was really interesting. She's a really interesting person. So her parents were Egyptologists, and so I think she grew up kind of around a lot of ancient mosaics. And there's sort of this beautiful, I'm going to make an accidental pun, there's this lovely symmetry in that she spent her sort of childhood looking at mosaics and repeating patterns and then went into crystallography, which is basically a field entirely about repeating patterns because a crystal is any material that is made from a repeating unit over and over. So you can have a crystal of anything if you line up repeating patterns over and over. So yeah, there's sort of something nice about the fact that she found that connection from Egyptology to to biochemistry and studying medical proteins.
Very, very, very cool. I'm just nodding. Sorry, listeners. So that used to be done with X-rays.
Mm-hmm.
You mentioned synchrotron light. What is the
Yep.
difference?
So what we do at the synchrotron is produce really, really bright X rays. So, X rays are just light, like visible light, but they're higher energy than the light that we see. So, you've got kind of your spectrum of light going from red up to violet, sort of getting more energetic. And then you've got your ultraviolet. So that's the stuff that will give you a sunburn. This is why I don't go outside. And then above that, again, you have X rays. So when you have an X-ray taken in a doctor's surgery, really what's happening is you're just being blasted with really, really energetic light. What we do at the synchrotron is extract really, really bright light from an accelerator. So we accelerate electrons around the donut, and every time one of those electrons whizzes around a corner, it loses some of its energy, right? It's sort of decelerating to swing around the corner. But we know we can't create or lose energy in physics. So that energy is released in the form of really bright X ray light. And that's what we capture and then funnel through a series of optics, so different mirrors and lenses and all kinds of things to bounce it out of the donut and down into the instruments that we have set up for different samples.
So that light is more energetic than X-rays?
The light that we can go quite high energy X-rays, but we sort of top out at X-ray. But they are very, very bright in terms of we have a lot of photons. So photons are sort of our packet of light. It's the particle, light's a wave, it's a particle, it can't make up its mind. And photons are the particle version of the light wave. And the synchrotron can produce just numerous photons. And then with the technology that we've got, we can concentrate them down to a very fine point, sort of just like you mentioned, focusing light with a magnifying glass, ideally not onto ants or anything like a psychopath in a, in a playground. I didn't used to set fire to twigs and things in my backyard using a magnifying glass, definitely not. But it's exactly the same premise. You sort of find that focal point and you can create a really bright, hot, tight jet of X-rays that perfectly matches the size of the sample you want to look at. And that's a lot more effective than what they would have been doing back in Dorothy Hodgkin's day, which is using, less energetic X-ray sources. So they could generate X-rays using electricity and witchcraft or something. I don't know, but definitely not with a synchrotron.
No, no. And the whole processing power and everything wouldn't have been there either. Is it what I'm sort of trying to visualize
Mm-hmm.
is obviously you've got different wavelengths of light, which different heights in how we think about them. And you've got teeny tiny things that you're trying to look at. Is the wavelength of the light relative to the thing you're trying to look at? Is that an important factor? Like, if the wavelength was too big, would it just miss the thing?
Absolutely, 100%. So yeah, that's exactly what allows us to resolve these really small distances between. In our case, we're looking at individual molecules. We're looking at the distances between atoms in those protein molecules. The only way we can get that sort of resolution is that the wavelength of X rays being very high energy. So it's this inverse relationship where you've got high energy, which means small wavelength, whereas radio waves, for example, are low energy, long wavelength. So a radio wave can just sort of pass on through the earth if it wants, whereas X rays, with their very, very high energy, short wavelength, that wavelength, pretty much the energies we use match up with the distances between atoms in a protein structure. So that's how we have that visualizing power of being able to see. I say see in inverted commas. What we're doing is collecting data and building a model, but we are essentially seeing the individual positions of atoms in those molecules. Yeah.
It's mind blowing that you can do that. One of the things that I occasionally worry about is one of your electrons escaping.
Oh,
Is is that a thing? Should I worry about that?
oh, you should. It's always a worry when the electrons get out. We like to keep them inside. Do the electrons escape? They definitely run out of energy and they run into things. So, electrons, very, very small, very light, and they crash into things and then they sort of do their whole electrony move through the atomic orbitals of the things they crash into and off they go. And part of what we have to do at the synchrotron is reduce the number of things that the electrons can crash into. So we essentially suck all of the air out of all of these tubes that the accelerated electrons run through. So the whole place is under, so the whole place is under vacuum. There is air for the users and the scientists. The tubes where the electrons are under vacuum to minimize the amount of collisions with air particles and different molecules. So that's a really important part of it. The other thing is that the accelerator scientists essentially use huge banks of magnets to really carefully focus the electron beam. So, because electrons have a negative charge, you can manipulate them using magnets. They, will be attracted to the positive charge of a magnet and repelled from the negative charge. So, our accelerator physicists can build systems that actually focus the electrons to try and keep them running down the track rather than crashing with the side of the tunnel and dissipating into whatever it is that the electrons dissipate into, just sort of wander off into other material. But we don't have them escape outside of our big concrete tunnels, not directly.
That's really the question I was asking.
Oh yeah, no. Look, people worry about particularly the radiation as well from the synchrotron. The whole facility is really carefully monitored for radiation. We have the electrons in a huge cement tunnel. So they're inside their own little vacuum tube, and then that tube is housed inside a big concrete bunker. And then the X rays themselves, because they're also radioactive, they are only ever used inside sort of lead containers. So they look like big teal shipping containers, and they have special systems to ensure that the X rays can only be switched on if the door is locked and that you've verified that there's no one inside. You can't lock your colleagues in and irradiate them. We have systems in place to prevent it. So don't even think about it. And that way there's never any crossover between radiation and people who do not want to be exposed to that radiation.
I'm glad to. It's not surprising that there's a lot of security and like safety in place. Is there any particular things that you're working on at the moment that you're really excited about?
Yeah, quite a few at the moment, actually. So we are in the process of building a new instrument. We're building quite a few collectively at the Australian Synchrotron, but I'm specifically on a team building a new beamline. So we call these instruments beamlines because we're really creative, and they're beams of light that are coming off the donut in a straight line. So beamline. And we're building a new one. It's going to be called MX3 because we've already got MX1 and MX2. And the MX stands for macromolecular crystallography, I think. No one's pointed out crystallography doesn't start with X, but that's okay. It might be macromolecular X-ray crystallography, potentially. But that aside, we're building a brand new one, and it's going to be very different and very technologically swept up our older beamlines. So the kinds of science we're going to be able to do with this new instrument sort of really exciting aspects of crystallography where instead of taking a single snapshot of one crystal that you've grown and getting a 3D structure, we will hopefully be able to do things like monitor a chemical reaction as it happens by taking lots and lots of rapid snapshots of lots and lots of different crystal. We want to be able to look at really small samples. So there's always this size limit with crystallography. You have to physically grow a crystal of the molecule you want to look at. And that can be challenging because proteins are big and squishy and they're usually suspended in water. They don't really like being told to line up in these neat, orderly patterns. So, students can spend years trying to crystallize a protein, and, tears into the crystallization buffers sometimes help. But what we want to do is have this new instrument set up so that really, really small samples can be studied as well, which means that you don't have to spend that huge amount of energy, psychological energy, growing these big crystals that are sufficient for the experiment. You can bring in your little piddly, not so great crystals, and the instrument will be bright enough, it will be energetic enough, it will be focused enough that you can still get meaningful information out of those small samples.
It sounds awesome. I'm
It
also
is.
assuming, well, obviously it is. It involves a synchrotron, but also presumably there's some proteins that would just never do the right thing and be like a nice structure.
Yeah, yeah, definitely. That's a big problem with the field of structural biology as a whole. So, structural biology is kind of what it sounds like. It's investigating biological systems by looking at their three-dimensional structures and learning about how they sort of physically interact with each other and with small molecules. And there are a few different ways of doing that. So crystallography obviously is the best way. I have to say that. I'm a crystallographer, but it is sort of the most historically kind of vanilla technique. It's the thing that's been the standard for the longest. But there are other techniques as well. So cryo-electron microscopy is one that's really taking off at the moment. So that's people actually being able to visualize molecules using an electron microscope, and they're actually starting to get structures to a similar resolution that we see with X-ray crystallography, which was always sort of the big gap. They could see blurry outlines of a protein where we could see individual atoms, but now cryo-electron microscopy is getting to a point where they can see that atomic resolution as well. And that's a really good technique for proteins that won't crystallize because you don't have to grow a crystal, you just have to put your protein onto this tiny little microgrid and then take a bunch of microscope pictures of that grid and then sort of stitch together the images that you get. So that's really cool. People also use techniques like NMR, nuclear magnetic resonance, to look at protein structures. It's a really dynamic way of looking at structures. One of the critiques of protein crystallography is that you're looking at a very static, maybe unnatural order of your proteins because they're all stacked in together, shoulder to shoulder, in that nice, compact crystalline form. Whereas in your body or in an organism, proteins are kind of flopping about in solution. They're in just a big salty bag that is a cell. So being able to see how they move in more detail with something like NMR can be really valuable too. Well, you can see some sort of motion in crystal structures as well, but it's a bit more like if you imagine taking a photograph of someone running and getting sort of a blur of where they are. Actually, I saw a tweet, I wish I could remember who it was, but they included a picture of their dog wagging its tail in one of their presentations. So there's sort of this beautiful blur where the dog's tail is wagging. And that's sort of the perfect analogy. You learn a lot about the range of motion of the protein of the tail. You learn a lot about how fast it's going, all from sort of a blur where that motion's taking place. So I think that's a really nice way of visualizing protein crystallography. Anything to do with dogs is, yes, that's a helpful analogy.
Fantastic. I'm very curious what an average day at work looks like for you. What is a day like at the synchrotron?
So an average day of work at the synchrotron, it's it's super varied. It's sort of hard to pick an average because I think one of the things a lot of people there love about it is that it is so varied. So, for example, today's a really good day for it. I sat in a lot of meetings, which I think is pretty standard for a lot of jobs, just Teams meetings all the way. And then one of my colleagues who works on the powder diffraction beamline, and one of my other colleagues who works on the X-ray fluorescence microscopy beamline. They came to my beamline and we loaded some micrometeorites into tiny little nylon loops using beeswax, and we shot X-rays through meteorites. And this was sort of kind of just a spur of the moment thing. We just had some spare time and thought, oh, why not shoot X-rays through meteorites? So that's sort of very much the vibe at the synchrotron. You could spend a day writing a report or doing sort of spreadsheets, or you could have a day where you are looking at space rocks and then a giant box containing a robot arrives and you have to unpack and start putting together a robot. You have days where you're sort of wading through floodwater, trying to figure out why one of your water pipes has popped. It's really varied, and it does depend on what interesting things your colleagues are doing and how much of a disaster there is at your instrument at any given time, whether you need to be putting out fires or doing development. Yeah.
Okay, so a little bit of everything. It does sound very collegiate, though. It sounds like
Yeah, absolutely. Yeah. I think that's one of the really fantastic things about the facility is that so by the time the building works are finished with all the new equipment, I think we're going to have 20 different beam lines. So each of these beam lines is an instrument perfectly tuned to a different type of science or sort of a different analytical technique. So we've got instruments that do microscopy, so taking really detailed pictures of very, very small things, looking at the elemental composition of them. We have people who are studying kind of surface science by shooting longer wavelength X-rays. We've got people looking at diffraction of powders and clays. Basically, any sort of analytical technique you can think of, there'll be an instrument that is doing that technique. And the result of that is that we have scientists in the building at all times who are experts in just completely disparate fields. So, we've got the meteorite people, but then we've also got dinosaur people, and we've got cheese people, and we've got lipstick people, and we've got rhinoceros plastic surgery people, and we've got newborn baby lungs people, and we've battery people. There's sort of a little bit of everything, and you often find that the sort of science that you do overlaps in really kind of unexpected ways with other people's science, which is really nice. So yeah, it definitely pays to kind of talk to your colleagues and see what they're up to and what interesting samples they've got on site that day, because you end up holding bits of the moon or Mars or seeing dinosaur fossils, and it's just, yeah, it's a little bit mind-blowing sometimes.
it sounds like what science is supposed to be.
Yeah,
But
yeah,
yeah.
I totally agree. I think that a lot of people who start working there coming from academic backgrounds or coming from the university system. And a lot of people are still, interlinked with the university system. Everyone kind of continues their own independent research in addition to supporting these instruments. But I do think I definitely personally felt that it was really nice to be on a team with like a focused goal and you're all working towards the same goal rather than being in a lab having one little bit of a project. Perhaps, I know some labs have a real competitive streak where there's less of a collegiate atmosphere and more of, people are competing to do the best science in the lab rather than necessarily building each other up. I'm lucky I've not had that experience directly, but I know that that's a real issue. So yeah, it sort of feels like a bit of a safe haven coming to the synchrotron and being around people who are just genuinely enthusiastic about what they do and about using their expertise to build other people up. Yeah, I think it's definitely a really nice environment.
And that leads on to a very important question of how did you get there? Like
How did I get there?
what what was your, say, plan from high school
My,
versus like what's actually
oh,
happened?
imagine having a plan. What was my so I in high school I studied science. I studied physics and chemistry, and I was, interested in it. It wasn't sort of the be all and end all, but I was also studying a lot of English, which I was more interested in. I think I wanted to be a film director for a lot of high school. And went to uni, continued to study science. I started to just fail out of everything. So, physics and maths, I suddenly was kind of hit by, oh, wow, this is a lot more complex at university level. I hadn't really learned how to study. I was, kind of coasting by in high school on being interested in stuff and it kind of just happening. But then when I got to uni, it was a bit of a culture shock of, oh, there's a lot of really smart people here and the work's a lot harder. So I definitely had a bit of a struggle for the first couple of years. I stopped taking physics and maths, which was really disappointing because that's what I really enjoyed. And I sort of went all in on chemistry, which I was less keen on. But after a couple of years getting my head around how to study properly and what techniques kind of worked best for me, I started enjoying the chemistry a little bit more and I ended up doing an honors project which started to kind of skew in that biochemistry direction. And that's when I started doing crystallography and I actually started using the Australian synchrotron as a researcher. I never went to the synchrotron. I accessed it remotely. So one of the really cool things about the crystallography beamlines is that you can load your samples up into a robot and the robot mounts them on the instrument for you and you can collect from your house at 3 a.m. in your pajamas if you want. And so that's how I did my honors work and my PhD work was sort of purely remotely. The synchrotron was a very abstract place for me. And it wasn't until I was a couple of years into my postdoc in the UK. So I went over there to join a research group there. And there's a beautiful big synchrotron in the UK called Diamond Light Source. And I was using that remotely as well, sort of sending off students' crystals. I was helping a lot of the PhD students with their projects. So I was starting to do less and less of my own individual research and more of that kind of support role. So teaching them how to use equipment, setting up their experiments, helping them with sort of planning different crystallography experiments. And yeah, the result was kind of realizing, oh, wait, the bit I like about this is the crystallography and the instruments and, the technical side of things. So it was that almost that physics coming back, which was what I was interested in the first place. And when the opportunity came up to move back to Australia and start working at the Australian Synchrotron, it was kind of like the dream job because I got to actually meet these beamlines in person, which I'd done my whole PhD on, but had never actually seen. So it was sort of weirdly emotional going and saying hi to the robot and seeing how everything's actually set out. And yeah, I think just from there, getting back into the stuff I really liked initially, that physics and maths and, how does light work and how does it interact with materials, and that's all the stuff that I really enjoyed and then kind of failed out of and then looped my way back into the long way, which was, yeah, I showed them.
I do love a long term loop that comes
Oh,
all the way back.
yeah. I think one of the things that I noticed a lot about kind of telling this story, especially to other students, is I had some students the other day who were saying that their takeaway from it was that this idea of science being like three different disciplines, like physics, chemistry, biology, is really artificial, and it's sort of purely something that is used in school and at uni maybe to kind of sort you into different clubs. But realistically, what we do at the synchrotron is we use physics to investigate the chemistry of different biological structures. So, the three are actually the same thing. You're just kind of approaching your viewpoint slightly differently depending on what angle you're coming at it. So it's really nice to kind of come back to a place where, the three are united again rather than in sort of separate silos, I think. Yeah.
Yeah, and it does feel like you kind of have to join a club when you're in high school. Like, oh, you're one of the physics people kind of
Oh,
thing.
big time.
Yeah.
Yeah. And, I get
Gosh
that it's a
forbid you
practicality and
be.
it has to happen that way. But, it's temporary. Don't give up your love for one discipline just because you feel like you have to kind of focus in on another, because you'll always find a nice overlap, I think.
And it doesn't just sound like you found the overlap, but you're the overlap like at the bleeding edge of how these things can overlap and support each other.
Yeah, and it's really nice, I think, even incorporating new, like completely new things. So, on the big list of things that I I do on my average day at the synchrotron, I've started to get quite into graphic design and computer stuff, user interface and user experience design, because part of our new instrument is that we have to have ways for people to interact with the instrument, right? So we need to have systems in place for them to steer the robot, to check their results, to log into a system and navigate to where they stored something previously. And so getting into the kind of nitty gritty of databases, and then also the front end. So, what's actually going to be a user friendly experience. I've sort of snuck my way into the into the scientific computing team at work a little bit to start doing a little bit of that, because we want our users to not only get really good science, but also we don't want them to be, I guess, distracted by difficult interfaces, or one of the things that can get, I think, a bit stressful for users who come to the facility as outsiders who want to use the equipment is that it's a 24-hour facility. They'll be sitting at a big bank of computers at 3 a.m., completely sleep deprived, trying to figure out where their mouse pointer has gone on 6 different screens. And then they've got all these thousands of windows that they have to click through. So, yeah, something that I've kind of discovered recently is wanting to kind of smooth that experience a bit. And yeah, it's super cool to be in a position where that can count as my job. Like it's not something I'm sort of doing on the side. It's something that's been incorporated into my actual role. So yeah, getting to learn the science of user interface design is also quite cool.
And that's a whole other world.
Oh yeah.
And it's really easy to discount it, but it's so important.
Oh
Like,
my gosh. It definitely is. Like the more I start looking into it, the just I have so much respect for people who can make things not look garbage. Like just trying to fit 1,000 buttons onto a screen without them making your eyes bleed. It's like, oh wow, there's a real skill to this. Like there's a lot of science that goes into it, and I found all kinds of websites where people have been doing, user experience experiments and incorporating all this data into their design. And yeah, it's this new rabbit hole that I need to sometimes climb out of.
because it does sound a little bit different to the other things.
Yeah, it's a good sort of. I think that's one of the big things about the synchrotron is that you never get bogged down in one thing. You can always sort of find something else that's equally challenging but is refreshing because it's differently challenging. So yeah.
New problems.
Yeah.
Is there any advice that you wish you could give to young Eleanor?
Wear bright colors. Yeah, I think a big thing I reflect on is that self confidence thing. I definitely felt the imposter syndrome in a massive way in my academic positions. So, all through uni and PhD and postdoc, there's this real sort of cultural pressure and this pressure you put on yourself to know everything and to be across everything. And it wasn't until I started at the synchrotron that I could kind of throw a lot of that off. And the real reason for that is that because what I do now is at such a specialized facility, when I started in the job, there was absolutely no assumption that I would know anything about it. Like everyone was quite open about the fact that this is completely new, like you're going to have to learn it all. We're always learning here, ask questions, break things, fix them again, ideally. Yeah, that assumption that, of course, you don't have to know everything. And that was really freeing, I think. You still have days where you feel the imposter syndrome creeping in, but it's definitely not a dominant force in my life anymore because I'm perfectly happy to just lean into not knowing anything. I'm very happy to sort of go to my boss and say, hey, this really fundamental thing that is at the basis of everything we do. Please explain it to me. And everyone's just completely fine with it. So yeah, I think advice I would give to younger me would be, when you're ready to kind of be okay with not knowing stuff and being genuinely interested in learning and asking questions without feeling like people are judging you for it, like that's going to be really freeing. It's going to take a lot of the weight off. And yeah, I did wear a lot of dark kind of colors to blend into the background when I was younger. And I can remember the first day I wore this like ultra bright rainbow jacket to uni, and I was like beetroot red the whole day, just so embarrassed. I was kind of like forcing myself to wear it. And yeah, I look back on that like, oh, sweetie, like I wear glitter to work now all the time. I've got sequins everywhere, like just yeah, confidence. That's the key.
And I think those two things are kind of related,
Big
but
time.
the confidence to ask questions, like that does not come easily. That's something you, yeah, have
It's something
to.
you have to practice at. It's like anything, you do have to practice putting yourself in that vulnerable position of saying, hey, I don't get this. And I think one of the things that helped with that was reframing it a little bit in my head. And this was something that really came about from teaching. So I taught chemistry while I was doing my PhD. I was sort of teaching first year and second year chemistry. And by reframing it, how do I say this without sounding mean spirited? If someone explains something to you and you don't get it, it's on them. Like that's that's their bad. They need to find a way of explaining it connects with you better, or they need to work on how they've communicated the idea. As a teacher, that sort of became the focus, right? If you try and convey a concept to a class of students and you know 2/3 of them don't get it, then you've miscalculated how to communicate that. And so I guess for any younger people listening, try your best to reframe it in your mind that if someone gives you an explanation and it doesn't click, then that's perhaps more of a comment on their communication of that idea rather than on you having something fundamentally wrong with your understanding. Spin it back on them and say, all right, you've tried, try again. Try to explain it to me again because that one didn't work. And yeah, take a bit more ownership of the fact that they have a role in that communication as well. And then it's a two-way street, so give it back. If you're then explaining something to someone, you've got to put the effort into making sure that you're explaining it in a way that works for them. So if we all kind of build those skills up, I think that really helps across the board.
I think a lot of the world would be a better place, to be frank. Oh, it'd be so much better. Are there any particular myths or misconceptions that you've come across, say, about working at the synchrotron when you tell people? Are there any myths?
I've definitely come across some really weird ones, like really weird. There's a YouTube channel that I won't name that did a an expose on the synchrotron because they're convinced that we're actually a portal to a demonic, which was super cool. Like it was during lockdown and we were just like, oh, this is exactly what we needed. They obviously couldn't get into the grounds because it's a facility. You have to have a swipe card to get in. So they were sort of just driving laps around it, filming it and burning sage and stuff. And I was like, oh yeah, we do have some negative vibes that could use some sage burning. Thank you. That was a really strange one. We are
That's quite
not a
extreme.
portal to the underworld, although some days it feels like it, but it's really not. I think more on the sciencey side of things, like the big one that we kind of got a little bit of the tail end of was the LHC stuff. So when the Large Hadron Collider was switching on again, it always brings up a little bit of a buzz around, oh, they're creating black holes. And that's wrong for a couple of reasons. The first is the synchrotron isn't a collider. We're not smashing things together, we're just sending particles in one direction. So even if you could make black holes by colliding particles, we're not doing that in Melbourne, so don't worry. But yeah, so we do get some interesting emails and letters in to especially our physics team, kind of asking about whether we're making antimatter or black holes and things. And like if we were, we would definitely be in the media more and would have probably some Nobel prizes. So I'm absolutely all for it, but it's not happening, unfortunately. No black holes at the synchrotron. I think from our user community, maybe one of the misconceptions is that like us beamline staff are either purely just names on emails. Some users, because we only see them remotely, we don't get much of a chance to interact with them. And I think it comes back to that same thing of people are sometimes a bit afraid to ask us questions. So a lot of the time, researchers will be there using the instruments and they won't necessarily be getting the best out of the instrument because they're doing it in a way that maybe they were shown by their professor, X number of years ago. And they don't want to seem like they don't know what they're doing, so they don't want to ask us for any help with their experiments. But like we are desperate to talk to people about their science. That's why we do what we do. We've been in lockdown for a couple of years. It's hard to get us to shut up about science. So if a user comes in and has questions about the optics or the instruments, like that's the happy place for instrument scientists. So respect your technicians and your instrument scientists and ask them questions because they know what they're doing and most of them are just really keen to help.
That was quite a spectrum.
Yeah, everything
Uh,
from ask questions to burn sage to keep demons away.
yeah, yeah. And I mean, obviously, asking questions is very important. And,
Hmm.
I'm sure you do your best to create like a safe feeling environment. But, like, no offense, but from the outside, the synchrotron kind of looks a bit dry.
Hmm.
It doesn't, and it's also almost in the middle of the city. It
Hmm.
doesn't really, to me, inspire conspiracy.
Yeah,
But
it's
each to their own, I guess.
yeah. I think that's why we were so excited by this by being in a little conspiracy video. It was quite a buzz for us because yeah, it is kind of just a big facility next to a university. It's up across the road from Monash. There's a big sign up saying Australian Synchrotron. If they wanted to like come into the if they wanted to come to open day, we just had our open day last month. We had 3,000 people come through, which was awesome. And, see the instruments and talk to scientists and different educators. And I don't remember seeing the demon hunting ladies there, which was a real letdown because I did invite them. But yeah, I don't know. Maybe they weren't feeling sort of energetically up for it.
Or maybe they're just wiser than we realize.
Yeah.
Keeping their distance. Golly, this is the first time demons have been mentioned on the podcast. Who would have
Oh,
thought?
amazing. I'm so glad.
Now that we've covered quite a lot of ground, but is there anything else you'd like to take this opportunity to share?
Oh my gosh. What else would I like to share? Well, it is a bit like Christmas at the moment at our new beamline because we've I joined the team just a couple of months ago, but the other two scientists have been on the team for a really long time and have been basically designing this instrument from the ground up. And like when we talk about an instrument, it's 30 something meters long. It's not just like a microscope on a bench because we have to actually get the x-rays from the big cement donut, which is, 216 meters around. We have to funnel them down into our end station where our equipment is. So they've been building this thing in, 3D modeling software and CAD, doing all the engineering drawings and things and figuring out where each mirror has to go to bounce the x-rays the exact right angle to get them to where they need to be. And it's only been in the last couple of weeks that boxes of stuff have started arriving. So all of this stuff that was purely theoretical for them is now materializing. So we got our detector a couple of weeks ago. So that's the actual, back in the day when Dorothy Hodgkin was collecting data, that would have been the photographic plates that she was using, like exposing each one and taking it away. But we got our detector. It's $4 million worth of pixels. It's 16 million pixels and it can detect sort of 500 frames per second. So that's a lot faster than, putting in a photographic plate and taking it out and putting it back in, taking it out. So that was super exciting and quite nerve-wracking moving it out of its box onto the bench because it was the most expensive thing I've ever touched. Then our sample positioning system arrived, which just looks unbelievably futuristic. And my boss has just been like a kid at Christmas, kind of running between these boxes, sort of like, I want to see what's in this one, what's in this one. I want to unpack it. But he's not allowed to unpack them until the staff from the company that we bought them from are there because they want to have their people on site to help unpack and set everything up right. So, yeah, it's been kind of funny just watching him sort of run from box to box. Like, oh, now the robot's arrived. So, yeah, we got our massive box of robot today, actually. But we're not going to be able to open it probably until next year. But I really feel the sort of enthusiasm from these other scientists who have been doing all the theoretical work for so long and now suddenly they've got material stuff to play with, which, yeah, it's just, they're very excited. I'm very excited. It's great. We're big nerds.
And there's nothing like working with excited people.
It's great.
How long is it going to take to put together?
A while. So, well, it sounds like a while, but it also feels like not long enough. We are aiming at having, so we want to be able to shoot x-rays to our sample by kind of the end of next year. And then the hope is to have users, like researchers, come from other facilities at the start of 2024 to start using the equipment. So, it feels on the one hand ages away, but then we kind of look at the scope of getting a 2 micron beam of x-rays to hit a 2 micron sized crystal, and the amount of work that goes into trying to get those things lined up is going to be definitely enough to fill the next 18 months or so, for sure. Less than that, 12 months, oh god.
It sounds like a long time, but
It'll fly by.
and because we do actually unfortunately have to wrap up, do you have a shout out for us? A virtual high five from that everyone who's listening should give virtual high fives to someone or someone's who are just doing an awesome job.
What's a good virtual high five? I think that definitely if anyone's interested in synchrotron science and the physics of it, there's a book by a scientist called Susie Shea called The Matter of Everything. So she's an Australian scientist, Australian, and I think she works between Melbourne and Oxford. I'm partly saying this selfishly because I get a small shout out in one chapter because I spoke to her about the Australian synchrotron, which is really cool. And I haven't finished the book yet, but it's essentially looking at sort of big physics experiments and then how they impact on people's day-to-day lives. So something as big and obscure as the Australian synchrotron, a big particle accelerator. This book kind of goes through how those sorts of instruments and facilities impact on the actual technology and lives that we live. So I think that's a really cool book if people are interested in that kind of topic. So yeah, give Susie a high five.
Sounds like, because that's really important piece of communication, actually. Yes.
Yeah,
Massive high
absolutely.
five to Susie.
Yeah.
And also to your team and colleagues, because, you know, I'm excited for them and they
Ah,
deserve a high five.
yeah, we'll keep posting our baby photos and unboxing videos as we take photos of every single instrument as it arrives. So, stay tuned for more sort of gushing photos of, oh, look at our detector, so shiny.
It'll never be this shiny again. Love it. Thank you so much for coming on the show, Dr. Eleanor. This has been delightful, and hopefully everyone is now even more excited about the synchrotron than they were beforehand.
Thanks so much for having me.